139th meeting. So we've had quite a few. I'm going to go ahead and share my screen. Let me know if you can see it.
Yeah, it's visible.
You can see? Okay, great. So this is the coverage of last week when we met on the 5th of February, and last week we had Riff presenting floating neck pipeline, and basically going through the HLD and PR 655, and a lot of Q&A about that. So here, just a few snips from what we were doing last week and the pipeline behavior and the steps, per step, and of course, you have a summary of everything we did last week, and then the longer whole project and longer explanations of what happened last week, in case anyone's curious. So, if you guys have any requests or feedback on meeting notes, please let me know. And so we also had a TCS who has been trying to tackle issue 38. So, and we also talked about needing time to discuss redirect map in the future. So that's what happened last week. And then this week we have, let me see here. We have Devin here from the Microsoft Software Defined Networking team, and he's a principal level software developer to present the load balancer fast path ICMP redirection design update. So we have that today. I don't know if you wanted to share your screen, Devin, or if you want me to share.
Yeah, I can share my screen.
Okay, I'll stop sharing. So everyone, this is Devin. He works on the same team as Michael and is a partner team of the SONiC team. So.
All right, thanks, Christina. So
Yeah, no
thanks for
problem.
the introduction.
Mm-hmm.
So hey, folks, I'm Devin Jagesh. I see some familiar faces here, but for the ones who don't know me, I work in Azure networking team, and I've been working on the SDN disaggregation project ever since its inception here at Microsoft. I've worked closely with some of you before. I authored some of the early documents when we took on the effort to open source this project to the SONiC community. And today is actually going to be my first presentation to the community where we talk about the load balancer ICMP fast path redirection. So with that, I hope my screen is visible.
Yeah, it is.
Awesome.
Mm-hmm.
All right. So I'll in this talk we'll touch briefly upon why we need a fast path, what it does currently, what happens if it's not there. I will also go into some of the scenarios that use fast path. We'll see how the packet structure of the redirect packet looks like, what kind of fields we look into, and the kind of the decisions that we make based on that. And just to make sure we have a good understanding, I have some snippets of PCAPs over here that show what the pre-fast path and the post-fast path behavior is. And hopefully that's information enough that helps tie up all the entire scenario together. And lastly, there are a few knobs that I'm proposing to control the behavior in case things don't work as expected. And for our debugging purpose, we propose some specific counters that can give us the visibility into the platform of how it's behaving under fastpath and whether things are being honored as expected or not. So I have a pull request out for this. Thanks, Riff, for the review comments on this. I'll just share the link in the chat as well for folks who want to follow along. And with that, let's talk about what the behavior is and where we need it. So in Azure or in the cloud for that matter, if you have a workload that's interacting over a publicly routable IP address or an address that is highly available and highly load balanced, it usually goes over these SLB muxes. So on the left hand side, I have a source, that's a VM. On the right hand side could be any entity in Azure. It could be a VM, it could be storage, it could be SQL, who has a well-known address advertised via these SLB muxes. So whenever the source wants to reach to this destination, the address is resolved to one of the muxes that's advertising it, and that's the first hop of the packet. And this packet is also snarted with the public address of this workload, so that when the destination replies, it can go over the second source side mux that we call, that's advertising this address, and that's how the end-to-end scenario works, right? So there is one mux in the hop for both the outbound and the inbound packet. And while the mux has a huge throughput capacity, it's still a shared infrastructure, and it is it does have some physical limits. So the idea of FastPath is to avoid taking this hop via the muxes once we know how the mux has decided to route the packet to the backend. For example, if this is a load balance service, there could be multiple instances that can serve the same whip, right? So the mux decides how to load balance this specific traffic to one of those destinations, and once it has made this decision, it informs the source about what that decision was via an ICMP redirect packet. And with that information, the source can then bypass the mux and simply talk to the destination end to end without having the mux in the picture. And the same goes on the destination side as well. If the source mux sees a traffic coming through this guy, it will send a redirect packet to the destination and will attempt to make that traffic bypass the mux in the subsequent packets. So we'll go a bit deeper into this. Any questions at this point? All right, awesome.
No questions from me. I'll save mine till the end. Go ahead.
Perfect. Okay. So this describes how the VM starts communicating. I've resolved some of these acronyms used in this diagram, and also below in the document in this table. When we say VIP, that's the virtualized address. That's the one that the SLB mux is advertising. So when we say a source VIP of the source VM is talking to the destination VIP, these are these virtualized addresses that we speak of. And of course, when any traffic lands on the mux, it has a decision tree which helps it decide where to route this packet. It's usually based on what is the backend pool of that specific address, which means how many backend workloads VMs usually are able to handle that traffic. And also there is some notion of the current health state of those VMs. So SLB has some probes which help determine which of the instances are able to receive the traffic, which are not, and that goes into the decision that usually the mux takes to decide where to route that traffic to.
Are those just tables on the SLB device then? Is it like a lookup table?
Yes, it's lookup table, and it gets populated via two means. One is the control plane, that's the user intent, where the user says that for this whip, this is these are my backend pools, and then the other source of information. Of course, there's Azure metadata that helps it figure out where those specific backend pools are located in the physical network, so how to route the packets to those. And then the second part to the story is the immediate health state of those VMs, which also it's customer configurable to some extent. So customer can tell SLB how to figure out what the health state is, what ports to talk to, whether to make an HTTP request, whether to make a TCP request, and get that information. And all that feeds into this decision tree that that SLB uses.
Thank you.
So in addition to making that forwarding decision of the packet, SLB will send this ICMP redirect packet towards the source of the traffic, and that is this packet that will not only have information about the original packet, so it usually has the notion of the 5 tuple that helps identify the flow on the source and destination side, and then it also has the routing decisions encoded. We'll go deep into the packet structure in a bit. And just to make it clear, this while SLB usually often or almost always sends this redirect packet, there are cases where it might not. So it's possible that the redirect packet that SLB sent got dropped over FiNet. So when it still sees a conversation going via the MUX, it might send a redirect packet later on in the conversation. So there's no such rule that the redirect will be received just after the SYN or just after the TCP handshake. It's to be expected at any point in the conversation. It can come between the SYN and the SYNAC as well. It can come while we are transferring the payload as well. Currently, we only support fastpath for TCP, and UDP is not supported. And the way this works is this says that we have the 5 tuple encoded and enough information to forward the to let the source know what the decision was taken by the MUX. This talks about what the flow fix-up should be. And of course, once the flow is fixed up, the traffic will bypass the MUX. When we say flow fix-up, it's usually fixing up of the outer destination IP address. Usually, without fastpath, that outer destination it will be the MUX IP address. Without fastpath, it will be the after the fastpath has kicked in, that outer destination address will be the direct destination of the packet. So in this document, we've just to for completeness, we take into account that there will be 2 MUX for the WIP to WIP traffic, one serving the destination WIP, one serving the source WIP, but they could just be the same MUX instance as well. Each MUX instance sends the ICMP redirect independently. So there might be a case, for example, where this orange path has moved to fast path, but the green path has not. And maybe the green path moves later on in the conversation, maybe it doesn't. We try not to take dependency on that behavior. So the fast path in either direction is independent of each other. And receiving ICMP means only the specific WIP must be fixed up. So I'll clarify the statement. I think this needs some clarification. Usually tries to send it to both source and the destination, the ICMP redirect. Of course, it's not a guarantee. And it's not a guarantee that it will be just after the SYN or at any given point in the TCP handshake. This point says that it might get lost, so be prepared. The NPU or the DPU should be prepared to receive this ICMP packet anytime, as long as the flow is active. And usually
is there number is there a minimum number of retries to make sure that the redirect has reached both the source and destination, or
no?
There isn't?
The redirect is more when the MUX injects a redirect packet, it's more of a fire and forget. It will not retry to make sure that specific redirect made through, but if it realizes that the connection is still hopping over the MUX, that's when it may choose to send yet another redirect. So
yeah,
so there could be a possibility where you received one redirect packet, you switch the flow to fast path, but then even though you are on fast path, you immediately received another redirect packet. So that's a possibility because of the asynchronous nature of this behavior.
And is it both the source and destination have to have received a redirect for the fast path to be established, or one of them is good enough? Maybe the source, for example.
Yeah, good question. So let's bring this diagram back into the picture. So fast path for this outbound flow orange line versus the inbound flow green line are independent of each other. So it's totally possible that this mux has sent the redirect packet to the source, and the source is now able to bypass this mux, whereas this mux has still, for some reason, not send the redirect packet to this destination. So there could be a case where only one side of the conversation is on fast path, while the other side is still hopping over the mux. So directionally, they're independent.
Got it. And instead of two muxes here, it could very well be that the same mux is operating a redirect on both directions also, right? I mean, this picture shows two muxes. Okay.
Right. That's right.
Thank you.
Hey, Devin, there is a trade-off, right? The mux does a job of properly multiplexing it does the load balancing part. Now you take it off from the picture, then you are trading it off, right?
Yes. So
the latency part, you are trading it.
The idea is, so mux does the load balancing decision once for a TCP conversation, right? So the decision that it makes about that specific TCP connection, it is able to forward that decision to the source and the destination. And we'll talk about how from those ICMP redirect packets, we can extract what those decisions were. Usually this decision is always the outer address to forward the traffic to and the inner MAC of the workload so that it can accept the traffic. So once that decision has been transferred, the source can apply the exact same transforms that the mux had applied. So no data is being that decision is not being lost in the process.
Okay, I get you. Thanks.
And so with what we explained, obviously when the fast path kicks in, it only changes the behavior of the subsequent outbound packets. The processing of inbound packets remains unaffected. But just a thing to call out over here is the inbound packet. It's possible that the source that's sending you the inbound packet would have transitioned to fast path. So the outer source IP of that incoming packet might change. Usually we don't take any dependency, or this is not part of our flow tables, so it doesn't affect. But for fullness, I just wanted to mention it in case somebody has taken dependency on outer source packet for a flow.
I think, Devin, we may have to clarify that a bit, because we do have something called PA validation, right? So PA validation is based on the outer source IP. So if once we change to fast path, and if the outer source IP change, then is our expectation to be no need to do PA validation, or it just matches the connection and so forth. Yeah.
So for traffic that belongs to the VPC, I believe that's where the PA validation comes into play, because you always have the CA to PA mapping for any traffic originating within the VNets or within the VPC.
Yeah, but the thing is, if before the fast path, the CAPA mapping is to the load balancer VIP, right? And after the fast path, it is not, that mapping is no longer there. See what I'm saying?
I see what you're saying, but this point is specifically for the inbound path. So for example, if this destination was a VM and it was receiving this orange packet, the outer source would be the mux PA. And there is nowhere do we inform the workload about the mux PA. So there should not be any validation on this address.
Yeah, but think about VM1's scenario, right? It has a mapping with the with a destination as the mux VIP, right? Mux, which is like the mux PA.
Right.
Right, and then your CAPA mapping is to the destination VM, and the PA will be the mux PA. That's what is expected for the reverse PA validation, I'm saying.
So I see what you're saying. So when this VM is expecting this green packet, but you see how there could be two different muxes. So even though it sends
but
the
the
forward
source
packet
is
to this mux.
the destination mux, right, for the orange. the source for the green is the destination of the orange. You can see from that line, right? Source is 2013, 20, 54, 18, right?
Sorry, but this one, right?
The green one, the green one. Yeah, the green one.
On the
right.
Yeah.
I see what you're saying. I think, yeah, at least for these scenarios that take dependency on SLB, I think that we'll have to, if we've taken that dependency, then at least fastpath will break when it kicks in, because
so I think
the
that's
source
why
will definitely change. Yeah.
Correct. If the source change, then I think our expectation is you don't have to do PA validation once the flow is fixed up.
Right. Also, just for fullness, I'm not sure if we've covered this in the community before, but there are cases where this, how this source is snarted to the mux web over here. There are cases where we don't need to snart that to the mux web. It usually goes with this PA,
Correct.
even though the return packet comes via the mux. So that's why I say maybe taking this dependency on the SLB scenarios might not be might end up breaking a few scenarios in the future.
So Devan, Prince, right? What other validations need to be skipped or will be skipped once the fastpath is set up?
Yes, the only other validation is this NSG evaluation. So specifically for ICMP redirect packets, the inner MAC will be the ENI, the inner destination MAC will be the ENI MAC. But we don't subject this ICMP package to any NSG or the security rules or any ACL rules that might be programmed. I think that's the only other thing.
Okay, good. So this will not hit any of the whatever multi-stage ACLs. It'll bypass all of that, basically.
Yeah. Yeah, because this is considered to be a platform packet, so there should not be any mechanism for the customer's rules to interfere with this. So that's the reason for this. And yeah, I've taken a note about this outer source IP stuff. If there's any dependency, then yeah, Prince, I'll talk to you, and we'll find a way to address that.
So typically, right, Devin, for the MUX scenarios, so the PA validation is skipped, right, because of the trusted VNF configured that. So after the fastpath fix-up happens, I think that PA address will have the tunnel to the destination, which will have the PA validation done for that.
Right. Yes. That was kind of what my expectation was. So I at least I thought that for MUX scenarios, the PA validation, instead of PA validation, we'll do VNI validation from the list of known VNIs that we have.
Trusted VNIs, yeah.
Trusted VNIs, yes. Awesome. Yeah. Thanks for that, Arun. And yeah, so specifically I've listed what are the various GRE keys that are used in this ICMP redirect packet and how they map to the specific scenarios that we've described later in the future. And of course, it's only generated for TCP traffic for now. This section describes how the ICMP ICMP redirect packet looks like. These packet structures are straight from the RFC. In the V4, because we have the internet header with the original datagram header, this is enough for us to extract the 5 tuple of the flow that needs to be fixed up. And the ICMP V6 redirect packet comes with an extra redirect option because this packet did not have enough information. So the redirect option helps us to figure out what that 5 tuple was. And for both V6 and V4, the redirect option is only present in the IPv6 ICMP packet, not in the V4 one. And there is so that gives us the 5 tuple information, and then exactly for what transformations to apply, that is picked up from the redirection info object, which is defined over here. So usually it has the NCAP ID if any NCAP needs to be applied, and you have the destination address where the packet needs to be routed to, and the inner MAC that needs to be fixed up in the flow. And yeah, the PCAPs that we have below each scenario will kind of tie this all together. So in this document, I have talked about 3 scenarios. One is a WIP and or ILPIP scenario. This is where the VMs have their own public IPs or a load balance public address. Then we have the private endpoint / service tunnel scenario. This is something that I think we are more familiar with. And then we have the ILB scenario, because these 3 scenarios are kind of the different way in which FastPath operates today. So I'll start with the private endpoint scenario. Oops. All right. So yeah, just to go into the scenario for folks who might not be aware, this is the case where whatever our source workload is, that is intending to talk to a private endpoint address. So the initial packet that lands on the switch, the source is the VM's CA and the destination is the private endpoint address. And it's encapped with the outbound VNI VXLAN encap as it lands on the switch, and then the switch applies these transforms. It converts the inner IPv4 to a IPv6 address with a known prefix that is programmed by the control plane. I hope this is visible, else I can zoom in a bit.
Yeah. I can see.
Right, perfect. So in this first diagram, we're just talking about the original state, how we currently private endpoint is handled. The inner IPv4 becomes the IPv6. Ethernet is the MAC address of the ENI programmed over here, and then this is obviously a GRE encap packet. The GRE encap itself is on v4 with the private link GRE key. And when the MUX sees this, when the MUX detects this traffic going over it, it sends an ICMP redirect packet, which looks something like this. It will be a ICMP v6 packet. It will have the source and destination that was used in the original outgoing SYN. It has other parameters that help you figure out what the TCP port number was, and then this ICM this redirect info and the option is basically what tells you what the transformation is going to be for the subsequent packet. So the GRE key will be something. I think this GRE key is the same as the private endpoint GRE key. The DIP address instead of will be this 100.116. So notice that in the previous case, the packet was going to 52.165, but now the MUX is saying send the packet to 100.116 and use this as the inner DMAC. So the subsequent packet that the source sends will now be to 100.116. This is the transformation. This is the after the flow fix up, and obviously the inner destination MAC address will be the one from the ICMP redirect info as well. So that this makes it makes the destination capable of accepting this packet. Oops, I keep doing that. I talk about how to identify what the pre-fast path flow will be like. That's not a slide. Yeah. I talk about what the pre-fast path flow will be like with the private link GRD key in an IPv6 packet. What will be the format of the ICMP redirect packet? what will be the I think I forgot mentioning this, but the redirect packet that we that we receive is itself GRE encapped with a specific GRE key, as you can see in this one over here. And this GRE key of the redirect packet also gives us a hint about what the scenario was of the original packet. So I mentioned what the GRE key is for the ICMP v6 redirect packet and what all modifications we need to do to the flow. So for example, in the private link case, the GRE key is same as the GRE key of the pre-fast path flow. The outer destination address is picked up from the redirect info, and this is going to be a v6 address. And the inner DMAC is going to be the one picked up from the redirect info as well. And same is conveyed via these PCAPs. This is the original packet that was captured. The outer packet, as you can see, was 32.52.165. The redirect packet over here informed I was a bit too lazy to build a Lua file for this. I'll see if the one exists internally at Microsoft, but just to convey this information, I have the hex dump over here, which shows the entire ICMP v6 packet, and the specific fields have been called out. So where the source port is, where the dest port is, where the GRE key is. I specifically mentioned over here, do not use this GRE key because the GRE key was already figured out while sending the original TCP packet. So that's why the GRE key over here is the GRE key from the pre-fast path flow and not from the redirect packet. So that's something to keep in mind. And then, of course, what the destination will be, and then what the inner destination MAC will be. And with these transformations applied, the original packet becomes this packet. So yeah, as you can see, 80.30 is the MAC address, and then this is the 100.116 address. So that's how FastPath works for the private endpoint scenario. Before I move into the other scenario, any questions at this point?
So I think just to clarify that on the source IP of the ICMP redirect, right? If you scroll up, it is something called 555.
Oh, yeah. Over here, I chose 5555 as the MUX PA. So
yeah,
this is going to be the MUX PA.
So one question here is when this packet comes on the smart switch back, it's as if like we don't have any way to validate the truth of this ICMP redirect, right? Like it appears like it's coming from some random IP, which the smart switch is not even aware of.
Yes, that validation actually comes from these. So the identity of this ICMP packet will be that it will be a GRE packet. And there is this fastpath key, which we have a certain known values of fastpath key that are to be trusted. And those fastpath keys are used specifically for ICMP redirects, not for anything else. So
that is that 254? Is that the 254?
Yes, these are this 254 for this scenario, and then 253 for another scenario.
Okay.
So Prince, this may not be or may be validatable. So if we look at the inbound routing, the PA validation, if we say okay in the future we change that one to a prefix, then it might be like validatable.
Doable, right? Yeah. So my thinking is like this ICMP redirect as if it is coming from some random source also like seems like we are honoring it, right?
So that's not really random source, but it's like the MUX PA. But the MUX PA lives in the infra range because it's a PA. Okay. So it could be like validatable, but it's just like it may be slightly looser than the others. Like
okay. I think here I think our main focus is on the GRE key, right? Because it's that both 253 and 254 will become like a trusted VNI.
Yeah.
Believe, right? Yeah. Okay.
Yeah. Awesome. So this was a scenario in which the initial flow already had a GRE and cap, and the subsequent flow was just fixing up the values in that GRE and cap and the DMAC, right? But for fullness, I wanted to talk about this scenario as well. This may or may not be a scenario that is currently supported, but just the way this works is if we've ever taken a dependency where it's hard to come back from, I wanted to call that out specifically because over here in the outbound packet, there is no encap, but post fast path, we expect an encap to be added. So that adds a bit of a complication in this scenario. So this is for the VIP and ILPIP. VIP stands for virtualized IP address. ILPIP is instance level public IP address. ILPIP is usually assigned to one workload only. It's not load balanced. Whereas VIP is usually there is a pool of backend workloads where the traffic can be load balanced to, and both of them are routable over the internet. So the way this scenario works is the VM is let's say with CA 10008 tries to reach out to a specific destination. The switch is supposed to simply snat this CA to the routable address of this ENI. Usually it's the address of the MUX itself, and then just forward it to the destination. This destination will be advertised by one of the other MUXes in the platform, so it will be able to route the packet, and based on the destination VIP, it will be able to either send it to a destination without any change or load balance it to one of the backend pools, depending on what the state MUX has for this address, right? And when MUX sees this traffic, it sends an ICMP redirect packet to the smart switch, which says for this specific traffic, it will point to the 5 tuples. It will have the GRE key. This has a GRE key of 253, so that's how you know it's this scenario. And it will say what the encap information should be. So use the GRE encap, use the GRE key, for example, is 256 over here, could be any, this will also be one of the trusted VNIs. And instead of sending it to, and the outer encap destination should be this, and the inner destmac should be this. And the source of the outer encap it doesn't matter, so it'll probably be the smart switch DPU IP itself. So you see when the after this redirect is applied, the exact same packet coming from the ENI now has a GRE encap. The destination is picked from the redirect info, the MAC address, same as the MAC address, and then the GRE key is also picked up from the redirect packet that was received. So in this specific scenario, we are not just fixing an existing some addresses in the existing flow. We are asking the flow to change in a way where after fast path we now do an encap, whereas before fast path we were not doing an encap. So that's what we talk about over here. Pre-fast path is just a flow is just a traffic snatted. There is no encap. We will receive an ICMP packet with GRE key 253, and the post-fast path flow will ask us to add an encap. The GRE key ranges will be from. I'll scrub this information. The right thing to say over here is this will be the trusted VNI range, and what the outer destination address should be. The inner okay, so over here this is the pre-fast path flows inner outer source IP, and then the DMAC comes from the redirect info as well. And the same is called out in these, it is showed in these PCAPs as well. So this was the pre-fastpath packet, and we got this fastpath packet with the redirect info I've highlighted over here, and then the post-fastpath packet now had a GRE and cap, and then the destination switched to whatever destination was mentioned in this fastpath, that is 10.126. So it's now being sent to 10.126.
I think, Devin, maybe we should explain what is the scenario advantage that we are getting with this, right? So previously the packet was sent directly to 2069, and then it lands on some MUX.
Yes. Okay. Yeah. Good point. I can explain that. Actually, let me explain this via this diagram itself.
Yeah. So I think that part is probably missing. Yeah.
Okay, understood. Yeah, that's a good call out. I can add that to the doc as well. Let me just take a note. So the end-to-end scenario over here is, consider this blue cloud to be a load balanced fleet. So you have 10 different VMs over here, right? And when the orange packet goes to the MUX, now the MUX has to decide which of these 10 VMs it should send the packet to. So that when that MUX has decided that based on the health state and the backend pool and everything, it will add a GRE and cap, because it will add a GRE and cap specifically to make that packet routable to the specific destination that it has selected. The reason why that GRE and cap is added, so that that this is a GRE and cap that usually contains the outer source address, which is the PA of the destination that SLB has chosen. So without that, because the existing packet was directed only to load balanced WIP, this WIP is only advertised and only routable until the MUX. After the MUX, this destination WIP has no meaning. So in order to route the packet from the MUX beyond, we need to encap it with the destination address as the PA of the backend VM that the MUX has chosen, right? So that's why the MUX, it adds a GRE encap. And now, because this is a decision that MUX has taken, MUX has decided to add a GRE encap to a specific address. MUX will now tell the source VM or the source DPU that you need to add the GRE encap, and these will be the parameters of the GRE encap, so that when the fastpath packet is received at the destination, it will appear as if it is the MUX that has done that load balancing decision. So that's
but one thing is the same flow fix-up happens in the reverse direction also, right? In for the ILPIP, or it's only in this one direction.
In the reverse direction, yes, but that should be independent. For example, when the return packet goes via this MUX, it might send a redirect packet to the whatever the destination over here was, asking it to do some flow fix up. And so yeah, in that way, the fast part would kick in over here as well.
Okay, and it comes with the same GRE encapsulation back to the orange VM1, right?
Yes. Let me think about that for a second.
Yeah.
Yeah, it will be the same. Same as in there could be some differences. For example, let's say the workload over here was hosting multiple CAs, so one VM hosting multiple CAs. In that case, MUX uses different trusted VNI in the outer encap. So let's say the traffic going to one CA is encapped with VNI 1, it's going to other CA encapped with VNI 2. So the encap VNI of the GRE key over here could be different from the GRE key that is used in the other on the other side, because this could have just one CA, so a single GRE key can identify that, whereas this could have multiple CAs, so we need a host of 256 GRE keys to identify each of those individual CAs that the traffic is intended for. But even though that's the case, the idea is that both these redirects should be independent in nature and should not take any dependence on each other.
Yeah, I think that part I understand, but I was thinking about the GRE key and all in this both cases, what to be used from the after the fast path kick in. So yeah, I think I can look into that offline as well.
Okay. Yeah, I'll be happy to answer any of the questions. So feel free to leave comments on the PR as well. So that's one scenario I wanted to call out where we add the in cap.
What's the accounting requirement here? Counters and stats and things like that.
Yes.
Between flows in either direction, and then flows going through the mux and not going through the mux. Okay,
Yes,
yeah,
I have a section specifically for what counters will be added. We don't want visibility into, because not doing fast path can create load on the Mux platform. So we want visibility into how whether we are honoring fast path, how many redirects we skipped honoring, and the current number of fast path flows. So I'll go in a bit of a detail for this. Christina, I know we are coming to the end of the time.
Yep.
How do you want to go?
Is there a requirement for a fast path CPS different from standard VNet CPS numbers?
CPS, no. Because
I mean, when I meant CPS, I'm maybe overloading that word in terms of when a mux is in the flight and you're sending a barrage of redirects, which also hits the DPU. I mean, is there a requirement for the redirect consumption on the DPUs to say, okay, it has to be 5,000 redirects per second, or 50,000, or whatever that number is? Is there a requirement?
I see what you're saying. I don't think this requirement is. I don't think it's an official requirement that's called out at the minute. But let me think about that and get back to you.
So we are sending a lot of packets through the mux, and you're doing this TCP SYNs. And then for each of them, you are setting up these flows and sending a barrage of redirects that has to be consumed in either end of the devices here, right?
Yes. So, yes, you're right. So yeah, I'll get back with an official answer, but just in practice, right? These scenarios are not as CPS intensive as they are bandwidth intensive. So it should be. If you are saying that establishing the original connection will count as one connection, and then honoring the ICMP redirect will count as another connection when we do that CPS math, I think that will be an acceptable. I think that should be an acceptable way to go about it.
Right. Is there any measured data so far you may have, or is that something that's kind of still?
No, I don't think we have measurements on that.
Put it on the list for what we need to do. Devin, did you want to keep this PR open for a week or two to wait for comments, or what was your thinking here?
Yeah.
You need some time to go back and make edits.
I will make some edits. I believe I can come back with next week for the rest of the PR discussion.
Yeah, sounds great.
Meanwhile, if folks can go with the PR and leave their comments, I'll be happy to address it. And if at all we think that we have reached the fullness for the PR even before next week, so I can go ahead and post that as well.
Yeah, I'll put something on your calendar to come back just in case, because this is a huge body of work. Thank you so much. This is really comprehensive. Thank you for doing it, Devin.
Absolutely.
Yeah. Rest of the team, do you guys have any comments on this particular one? Q&A? I'll go ahead and share my, I guess I'll open it up to other PRs and issues and things. Satya, did you need help with your issue or anything that you are working on?
Hey, Christina.
Hi.
Hi. We are facing some issue while bringing up the SONiC Dash environment. I placed our concerns in the issue corner.
Yeah.
I addressed it to Chris. It would be great if anyone can help us on for the bring up process. I mentioned in detail what are the issues we are facing out there.
Yeah, I did see the email, so. And it's issue 38. Let me pull this up real quick. Okay, so here we go. This was what you were experiencing. So you're getting an error with the slave buster as a base image. Error in image APT repository. So you're looking for a solution just to bring up the environment.
Yes.
Okay. So do you guys think this would be a SONiC issue or more of like a test environment issue, I wonder? What do you think, Mircea or Prince?
I mean, it says that it's bringing up the build image with SONiC, with Redis, SWSS, sensing this. So this is more like a SONiC stuff. If it was from these repos, just a BMV2 standalone, I could have helped probably to get it running. But this seems more integrated, the integration in SONiC. So
yeah. Prince, do you have a pointer where I could point this, or is there a way to get help for things like this from the build team?
I think this is one of the work I believe Riff and team is doing to bring up VPP with SONiC build image, because here they are not looking for the actual hardware, right? It's basically the VMV2. So I'm not sure what is the latest on that project, but I believe they are targeting it to be available so that it will be part of the CI/CD pipeline, and the SONiC management test can run independently of the hardware. So I think it's better to tag Riff to get when.
Thank you. Okay, thanks a lot for that. And then I know we're getting very, very close to the end. The only other thing I wanted to mention is I think we might have a presentation in the Thursday Smart Switch work group. I think it's this week for the Smart Switch HA topology for physical testbed here by Jing. I think it's either this week or next week. And so I wanted to mention that. And got this. That's it. That's it from me this week. Anyone else? Okay, I will stop the recording and